Hi, welcome. This video is going to be a brief introduction to 2D hydrodynamic modeling using HEC-RAS. Now, it is assumed that you have learned how to perform 1D modeling using HEC-RAS, and I'm also going to assume that you know a little bit about open channel hydraulics and things like that, because I'm not going to go into details of all the equations and how the calculations are performed in 2D HEC-RAS. This video is going to be a very high level overview of what 2D HEC-RAS is and what we are going to do. Okay, so let's get started. As I mentioned, I am assuming you have already done some modeling using 1D HEC-RAS, and this is what you see here. So in one-dimensional HEC-RAS model, we usually define the geometry by using cross sections, which is what you see here. This is the main river and this is the tributary, and there are cross sections, and all the calculations are performed from one cross section to another in one dimension, and we get the average water surface elevation and velocity at each cross section. In 2 dimensions, instead of doing calculations at cross section, the calculations are done for each cell in this 2-dimensional mesh that you see here on the screen. And I'm showing you 4 arrows because all these arrows are directing water on the surface in 2 dimension, and the water movement in the 3rd dimension, which is the vertical dimension, is not included. So this is a 2D model that you see here, and sometimes both 1D and 2D are combined, and which is what you see here. And in the main channel, we are doing calculations at each cross section. So this is the one-dimensional part. And then when the water goes into the floodplain, we have a mesh, and this is the 2-dimensional part. So this is called 1D, 2D, or sometimes we also call this as 1.5D. But in this video, we are going to be focusing on the 2D modeling. Now, before we learn about the equations that are used in 2D HEC-RAS, let's learn a little bit about the terminology that we use when we create a mesh. So what you see on the screen is a mesh, and we have 1, 2, 3, 4, 5, 6 cells. So each polygon that you see here is a cell, which is what is defined here. And then you see these blue dots, so these are the center of each cell, and they are not necessarily the centroid of each polygon. If the polygon is a perfect square, which is what you see here, this can be the centroid, but for other polygons they are not centroid. Again, just remember that each cell is going to have a center, and that is where the water surface elevation is calculated. Then we have face. So face are the boundaries of our polygons. They can be a straight line segment, which is what you see here, or they can be a polyline, not necessarily a straight line, so a combination of multiple segments. And then finally, we have the face point, which is what you see here as red circles. So these are the vertices of our cells, and they are called face points or end points or nodes. So this is all we need to know about the terminology that we are going to use when we create a mesh in HEC-RAS 2D, but this is applicable to any 2-dimensional modeling where you create a mesh. So you have a mesh, and it's a group of cells, and each cell is going to have a center, face, and nodes. What you see on this slide is a regular mesh here on the left. Now, if there is no change in the topography, this mesh is fine. In the middle figure, we see that there is a structure here. It can be a road or a levee, and that is going to have different elevations compared to what we have on the surrounding topography. So in order to introduce these kind of changes on the terrain, we create what we call breakline, and which is what you see here in purple on the third figure to the right. And as soon as you introduce the breakline, you can see the mesh structure has changed. So when we create a 2D HEC-RAS model, we are going to use breaklines in certain cases. And if you want to define what a breakline is, it is basically a polyline that we can use to enforce cell faces along linear features, and these linear features can be road or levee or any high level ground or any kind of structure that has different elevation compared to the terrain that we are going to use to define our mesh. Similar to breaklines, there are also refinement regions, and as the name suggests, what we do by defining a refinement region is to have a different mesh resolution for that refined area. So on the top right, we have a mesh, and this is our regular mesh, and on the right, we have refinement region, and for this refinement region, you can see the mesh is very fine. On the bottom left, we have two refinement region. One is coarser than the original mesh, the other one is finer than the original mesh, and you can see we also have a break line here. So refinement region is an area where the mesh resolution or the cell point spacing is different than the original mesh that we created. So we are going to have mesh, and depending on the change in elevation, we can define break lines. And if we are going to have very high resolution modeling for a certain area, we can define that area by using refinement region. Now let's talk briefly about the equations that are used. What you see on this slide are the equations that are used in one-dimensional modeling. So we have the one-dimensional continuity equation, and then we have the momentum equation, and the momentum equation has acceleration terms and pressure and energy term. So this is the slide that I have explained in my 1D video for HEC-RAS. In 2D, we again have the continuity and momentum equation. So what you see on this slide is the continuity equation. Now this equation may look little different, but it is more or less the same. So if I go back, so what we have here is the change in flow area with time, but now instead of flow area, we have volume, change in volume with respect to time, and then the flow across the face that is equal to the sources and sinks. And what you see on the bottom is the finite volume discretization of this differential equation. So this is the continuity equation or the mass conservation equation, and then we have the momentum conservation, and in HEC-RAS, momentum is calculated normal to each phase, and these are the terms that are included in the full momentum conservation equation. So we have the temporal term. This is how it is defined in HEC-RAS manual, but this is local acceleration, convective acceleration. So we have Coriolis force here, then we have the pressure term, then we have the bed friction or energy term, then we have the momentum diffusion, we have wind stress. And if we think broadly, on the left hand side, what we have are the acceleration terms, and on the right hand side, we have all the internal and external forces acting on the fluid. Now this is the full momentum conservation equation, and when we use both the continuity and the momentum equation together, these are called shallow water equations or SWE. In HEC-RAS 2D, shallow water equations are used to solve for water depth and velocity for each cell and across the cells. And when we use the complete form of momentum equation along with continuity, it is called shallow water equation. Now, as we saw, the shallow water equations have all the acceleration terms on the left, and then we have momentum diffusion, and then we also have the wind stress term. Now, in many cases, these terms may not be significant. In that case, we can ignore those, and we are left with pressure gradient and bed friction. and this simplifies the equation a lot. And when we solve the momentum equation just for the bed friction and pressure gradient, we end up with this equation for velocity, where beta is a coefficient, and this is the expression for that beta. And when you use this expression for velocity into the continuity equation, eventually you end up with this expression to solve for the water depth and the velocity. And with this approximation, this equation is called diffusion wave equation, or diffusion wave approximation of the shallow water equation. Now HEC-RAS 2D uses both diffusion wave equation and shallow water equation, and depending on our situation we can select which equation we want to use. By default, diffusion wave equation is used, and we will talk little later when to use diffusion wave equation or the shallow water equation. So as I said, it is default in HEC-RAS but can be changed to shallow water equation. Now we know what equations are used, then the question is, how are these equations solved? Now both diffusion wave equation and shallow water equation use finite difference and finite volume methods. Again, assuming or hoping that you know a little bit about the numerical methods that are used in solving differential equation. So finite difference is used for time integration and momentum equation in HEC-RAS 2D. And as we saw on the continuity equation slide, finite volume is used for continuity equation. Some of the terms are solved implicitly. Specifically, the pressure gradient term is solved implicitly. Acceleration and diffusion terms are solved explicitly, and the other terms are solved in a semi-implicit fashion. Okay, so again, as I said, we are not going to go into all the details because it will be a very long video, and I hope that you know a little bit about numerical methods to understand some of these terms. Now, if you have done one-dimensional steady-state modeling using HEC-RAS, you may have never experienced numerical instability. When we do unsteady analysis and in two-dimensional HEC-RAS, you are going to face numerical stability issues if your mesh resolution and the time step do not satisfy what you see here is the Courant number. So Courant number is defined by this expression. So we have the flow velocity or flood wave velocity, then the time step, and the mesh resolution or the cell size. Now if this condition is not satisfied, you will have issues with the computational stability. And in order to make sure that we don't face this problem, we have to make sure that these conditions are satisfied depending on whether we are using the diffusion wave equation or the shallow water equation. So for diffusion wave equation, C has to be less than or equal to 2 ideally, but it can work up to a maximum value of 5. And if you are going to maintain a C value of 1, you have to make sure that this condition is satisfied. If you are using shallow water equation, you can see that the value for C is less than what we have for DWE or the diffusion wave equation. And the shallow water equation is solved in HEC-RAS 2D using two different approaches. So this is the Eulerian Lagrangian method. If you are using that method, then you can only go up to a maximum value of 3 for C. If you are using only the Eulerian approach, which is the most restrictive form, and here you cannot have C greater than 1, so ideally it should be less than 1. So as you can see that with diffusion wave equation, you have more flexibility in terms of time step and mesh resolution, and that is why it is computationally much faster, but the results may be less accurate in some cases because the diffusion wave equation ignores the acceleration and the momentum diffusion term. So just keep this in mind that the C value must satisfy these conditions depending on whether you are using diffusion wave or shallow water equation. Then the question you may ask is, how do we know what mesh size and time step to pick? Now mesh size is dictated by terrain properties. So if you have a very flat terrain, you can have a coarse resolution mesh. If you have a very steep terrain or terrain that is changing drastically at different points, you may want to have a mesh that has very fine resolution, or depending on how your area looks like, you can have a coarse resolution mesh, but you need to have refinement regions and break lines to incorporate the changes in elevations. As I mentioned here, if you have road, levees, flood walls, then you may want to include break lines and refinement regions. While we know the expression for Courant number and the conditions that need to be satisfied depending on whether you are using diffusion wave or shallow water equation, you cannot keep calculating that number. All you have to do is play around with different mesh size and time step and go with what works. So as I mentioned here as my last point, selection of appropriate mesh size and time step is a balancing act. So we have to make sure that we achieve numerical accuracy while also minimizing computing time, because you don't want to have very fine resolution and very small time step, because it will take very long for the simulation to complete. So again, as I said, you have to play around with the mesh size and the time step. Now you cannot play around a whole lot with mesh size, because that again will take time to construct your model. So many times we keep the mesh size, then we define the refinement regions, and then we play with the time step. And all this comes with more experience and more simulations you do. The final question you may wonder is what to use. Should I use shallow water equation or diffusive wave equation? Now I'm not going to read everything that you see on the slide. As I mentioned earlier, DWE is the default. Now even if you are going to perform a very complex simulation where you have backwater flow and tidal effects and things like that, you do want to use shallow water equation, but it is always a good practice to start with diffusive wave equation. Make sure that your mesh and the computational time step and all the numerical stability issues are addressed, and if you are happy with that, then you can change the equation from DWE to SWE, and that can be done very easily. So it is a good practice to start with the diffusive wave equation, which is the default, and then transition to shallow water after addressing any computational issues you may face when you run the simulation. Similar to 1D HEC-RAS model, so these are the steps that we have when creating a simple 2D HEC-RAS model. We are going to create an empty project. We are going to import the terrain or a digital elevation model. Instead of drawing cross sections, bank lines and flow paths, we are going to create a mesh and assign properties, specifically the Manning's N, and then we are going to provide boundary conditions, and finally we are going to run the simulation. And we have seen these files with 1D model. We have project file, geometry file, unsteady flow file, and plan file. Now I said simple 2D model. Even for the complex 2D model, the steps are still the same. The only difference is going to be the refining of mesh, more break lines depending on what kind of terrain and structures you have in your model, and also maybe different boundary conditions for each structure. So finally, this is what we are going to do. Now if you have followed the 1D HEC-RAS model on my channel, you may be familiar with this river, Wabash River, and the Tippecanoe. We did cross sections. In this case, we are going to do a two-dimensional mesh, and we have the boundary condition upstream for the Wabash River and the Tippecanoe River, and then the downstream condition for the Wabash River, and we are also going to define one bridge, and finally we are going to create this simulation to get this inundation. Okay, so this is what we are going to do, and in the next video we will start the actual modeling of this region using HEC-RAS 2D. So I hope this video gives you enough to know what 2D modeling is in HEC-RAS and what we are going to do in the next video. So this is all for this video. I will see you in the next video. Thank you. Bye.